So yeah, I have what you just said. You guys, I think I'll agree with that. The next thing I might encourage you to do, and I did encourage a couple of you to do this, is actually to write this out, right? It's a little daunting, I think, to come up with summation notation for this, but I think we'd all agree that that's what we're looking for. Yeah? Right? Now, the next question is, like, how do we write that in summation notation? There's a point one. There's, like, looks like, I think I challenged a couple of you on this. You said the sum is running from, like, 2 to 7. Well, no, it's not. Because we should be adding up 50 things, right? So definitely, like, we should be having to evaluate our sum 50 times and then add it up, the thing inside of our sum. So the only other thing we need to figure out is like kind of an expression to make this thing inside f of x march forward, right? Like if k is, now I saw different people do this different ways. How do you make the sequence happen? If let's say this is k equals 1, and this is k equals 2, and this is k equals 3, all the way up to k equals 50. If we're starting at 1, then this would be k equals 50, and this is k equals 1 and k equals 50. Yeah. Did you figure it out, Clemens?
Yes.
Okay.
So I said it was 2 plus parentheses k minus 1 over 10.
Okay. So yeah. So this feels like just something linear almost, or you might have used a word last year for that too, or other years. What kind of sequence is that? Yeah, it's just an arithmetic sequence. And the first term is 2. So I hear you saying that like 2 plus. And then say again what the other part was. 2 plus.
K minus 1 over 10.
Then the k minus 1, what is that?
We're indexing from 1 to 0.
Okay, so if k is 1, then that means we're adding nothing. It's just 2. All right, so I wrote something very similar here. But do you agree that I'm adding up 1 to 50? Now, this is the test. A lot of you, like, I think just kind of in the dark, just like kind of write down something. You're like, I don't know, this kind of feels right, or I hope this is true, or something like that. Is the sentiment when you write down summation notation. But the proof isn't actually like expanding it out. Does it work? Plug in k equals 1 and tell me, do you get 0.1 times f of 2? Plug in k equals 2. Are you getting 0.1 times f of 2.1? Do you? All right, then I think it's working. And then maybe check the end condition too. Plug in the last one, plug 50 in. Do you get 0.1 times f of 6.9? Yes? Try it. You don't have to, don't trust me. Does that seem to work? Stare at it until it makes sense. Go ahead. Say it one more time. Oh, yeah. Yeah, 0 to 49 with just a k here would be fine too. And yeah, a couple people did that, and I gave them a sticker for that too. Yeah, as long as you're adding up, as long as this is the sum we're talking about, then I think we're okay. Yeah. All right. Well, I think I kind of have warned you that this was coming a little bit. We'd like to talk about this more in depth now, even today, right now. We'd like to that is the essence of today's lesson, is understanding what you just did in the warm-up. And we're just going to unpack that a little more and practice with it a little bit and make sure you're feeling good about it. So let's just read together the introduction here. Zach, why don't you read the first paragraph? Yeah, does everyone have this in front of you? Should match. All right, how about you read the first paragraph? We'll get someone else to read the second paragraph. Go ahead. Listen as Zach reads.
Last we said that the definite integral was defined as the length of a sum of rectangles. This made sense because even though other shapes often provided good estimates, rectangles were easy to implement systematically. As we increase the number of rectangles, or equivalently decrease the size of each subinterval, we obtain an exact value for the desired integral. We use the following notation.
And there it is. And that's just, I copied that directly from a PowerPoint we had at one point. But that's not like real helpful in really doing what we're doing right now necessarily. So we're gonna try and like tease this out a little bit. So Albert, keep reading there.
But how does the variable n relate to the index of the sum table over the size of each subintegral of x? And how does this relate to the limits of integration a and b? In the following activity, you will explore this idea in more depth and obtain exact expressions for interpolating with precise notation.
Thank you. I see that. I see why that was good. That was good. Good. So I have an example ready for you here. It's this picture that's on there on yours as well, and I have it shaded underneath from -2 to 0. There's the picture of it. There's the expression that we know and love, and we should all acknowledge that there is no way we know how to calculate the area under that at this point in our lives, besides approximation techniques. So let's do. I don't mean to interrupt you too much. Let's just try to do 1 through 6 here. It kind of guides you through the process. In fact, and to some extent, kind of what you did in the warm-up. But you know, when you get to 4 and 5, you know, things get a little more interesting, maybe. So go ahead and with your table work through 1 through 6. And if I need to interrupt, I will. But I'm going to really try not to. I don't think you'll need a calculator really all for this. After. Now, on the first one, I'm not designing you necessarily to write it as a in summation notation yet. You're going to do that on number 2. I mean, if you're advanced and you want to just write it down, that's fine. That is eventually the point. Make sure you notice that we're asking for right hand.
That is not a template. Joe, did you do this?
One of you could write your answer up there too, it's different than other people.
for number 2.
Point five. Can you fit it in here? What do you guys? Anybody else have another answer on number 2? We have a couple answers that are coming up here. I like seeing all the different results we're getting. Does yours match one of the 3 that are up there? Or slightly different? You want to write yours too?
Yeah.
Verify if you didn't have these, verify the other ones are correct.
That's totally true.
We have another one, a 4th one coming up.
Where should I put this? Can I shoot above it?
Wherever you can put it, yeah. Let's enjoy the creative, what everyone has to offer here. Very interesting.
Oh, I get it. Oh, wait, is it just scale?
Oh yeah, yeah. You can put that.
Is it because of a joke? Am I a joke? Is that funny? Is that funny? Yeah, I'm out from it. It's a hole. Yes, 2 holes. Yeah. Which one do you drink?
All right, so do you see now there are 5 ways of people have writing to write this up here. I think they're all correct. Yeah, interesting, right? I'm gonna go off this slide in a minute, but I'll let you study it for another couple seconds. Yeah.
Can you explain how the middle one on the bottom?
Peter, explain your work. You put the middle one up, right?
Yeah.
Why does that work?
You're going backwards. So go to negative 1.5, negative 1, you go 0, negative 0.5, negative 1. You plug it in. You get the progression.
Yeah, so if you plug in 0, you get that exponent is 0. So he's like running it backwards just to be like slick and cool, like he wants to be cool. He wants to be cool, Peter does. But it is right, isn't it? It does work. It's kind of creative, but it does work. So there you go. Okay. Good. In the end, the test of anything mathematical here is like, does it work? If it does, then like you're right. We can pack up and go. You know, yeah. Go ahead, Rebecca.
Wait, so
You still talking about this one? We're still talking about this one?
We're trying to, wait, if you plug in 0,
You get 0 here as the exponent.
yeah.
And then if you plug in 1, you get negative 0.5.
Yeah, so if you, okay, when you plug in
And
0,
then-
then you get like 1/2, right? Because it's 1/2 times 5 to the 0. Which is that?
Yeah, so 1/2 is this thing out here, right?
Yeah, but when you like look at the graph, it doesn't match up.
I know, I think he's running them in reverse order than what you have, right? So you get 1/2 times 5 to the 0, plus 1/2 times 5 to the negative 0.5, plus 1/2 times 5 to the negative 1.
Yeah, like, so on the first, here. So like, the first thing you run and you go to. Oh, wait. We're stupid, okay.
All right. So how about for number 3? Let's see who had that one there. Let's get a couple people up here for these. How are we doing on this? Number 3 looks good. Something like that, right? Yours might be a little different. Oh my goodness. It's okay. I get it. Yeah, did you just, you're right, 0 is 7. So we're going to get points instead. Never comes over here. Alright, who has number 4? You wanna take that again? You know what I mean? Feel like we have it. Yeah, that is sure. Anybody have another These guys are going like reverse song, which are correct. I feel like they talk about them, but they are correct. I want to encourage creative thinking. Full disclaimer, the boys have been very creative. We're coming up. They are right. Rosa has like a slightly easier to read answer, so I'm inviting them all up. They're all correct, but okay. What's with the creative voice in this stuff? Yes, I am gonna like put a box around Rosa's, but I'm gonna say that. Yeah, to protect it from all those crazy
Oh, okay, I get it. Dude! That's weird. You're very
Can you put a box around your
Oh, sure. half of the
I'm representing our table.
Negative 1.5. Oh yeah, I was gonna say, wait, do we have, if you plug in 1, the first thing you want to get is negative 1.5, isn't it? And you do here, so that's, I think that's okay. Right? Don't you want to get the values, or no? Maybe we do need to start, actually, yeah, maybe this is not quite right. Sorry, Rosa. Here, let me, I think if we start with, what do we need to start with? Negative 2, right? Does that work? Try that now. I mean, if you plug in 1, do you get the first, like, delta x away from negative 2 here? If you plug k equals 1 in, so maybe correct yours there, right? Is that okay? I had to change it. If you plug in 1, then you'll get negative 2 plus a delta x, which is exactly what you want for the first rectangle. You want the right-hand endpoint of that first rectangle, right? The right-hand endpoint of the first rectangle is not negative 1.5. It's negative 2 plus whatever delta x is. So one copy of that, you know. So, all right. So I'll write this one. So the limit as n goes to infinity, then, right, is what we want for this, right? If you did it correctly, then you can just slap right now, slap in your answer for number 5 there, right? So from, how about from k equals 1 to n is, I'll just use the one Rosa had here, 1/2 times 5 to the negative 2 plus n over k, except it wasn't 1/2. Wait, what was it? 2 over n out front. And here this was 2 over n times k. All right, whew, all right, good. So I think we've done it. I think we've like just come up with an exact expression for this integral, right? Whew. All right, that is the main thing we want to get to you today, is like that you can do this. You have some tasks to do here before you have. I think we're going to skip the middle section of this because it has an activity for you to do with each other that I thought we had time for, but I was wrong. But then there are some problems on the back page, along with the problems on the second handout that I gave you. That I'd like you to like give a try. Yeah, do it all. Yeah.
Okay, so you said not part 2?
Well, part 2, you'll see, requires that you like make up your own and trade with a partner. It doesn't make sense on your own. So.
We skip all of part 2?
Right.
Yeah, so no part 2.
Yeah, no part 2. Part 3 on the back, though, you can do, right? Those questions. What? Yeah. Everything that you can do. Let me before we like dissolve completely. Let's try maybe one more together and make sure we're good on this. Let's do, I don't know, why don't we pick one from this handout, and I'll just kind of show you how my thinking would go on one of these. Number 4? Sure. So, for example, I'll do one of these for you, right? So if we can do this all at once, that'd be great, right? The limit as n goes to infinity of the sum from k equals 1 to n. It doesn't matter actually which we use, Rm or Lrem. They'll both in the limit converge to the same thing. So whatever. All right. So what is this? Is always going to be. Well, what's our change in x going to be this time? Well, it'll be 7 minus 3 is 4 over n, right? Times 1 over 1 plus x, which we want x to be incrementing along the way again. So this is where coming up with an arithmetic sequence that does the job is what I need to put in here. We're going to start at 3. This is like our x value right here. We're going to start at 3 and add delta x times k, right? And we already thought about what that is. So just verify that that does the job. Let's actually plug in 1. If you plug in 1, you get 3 plus 4 over n. Isn't that the right endpoint? 3 plus 4 over n. Isn't that the right endpoint of the very first subinterval? 3 plus 4 over n. That's 3 plus 1 delta x. And then if you want more of them, if you plug in k equals 2, you get the right endpoint of the second interval. That's 3 plus 2 delta x's, right? Where delta x, I mean, delta x is 4 over n, right? And just to check the n case, if you plug in n, what do you get? If you plug in n for k, like if k is n, then we get 4 here. That's 3 plus 4 is 7. Are we at the right place? Are we at the end point of the very last interval, whenever that comes, right? Yeah, we'll be at 7 then. Do you see how we can kind of make sure it's right? Yeah.
So you're saying it doesn't matter if you think about it
I'm using RRAM.
versus LRAM?
Yeah, you can do LRAM. It would just be.
What did you do?
I think this is nice. You could do 0 to n. I guess it'd be 0 to n minus 1. Well, yeah, 0 to n minus 1 if you're doing. Or you can do it this way, but then you'd have to modify. You could do k minus 1 in here too, right? Yeah, if you want to do LRAM.
You guys,
Right.
But
Doesn't matter.
Like, does it, in the end, like,
They
should
both
come out
converge
with
to
the
the same thing. Yeah, exactly. Yeah.